This is supposed to be a universal asynchronous 556 transmitter receiver, but actually it's just a transmitter, so I guess you could call it a UAT, not a USART. So basically what we have is a set of these 556s. Of course, each one contains two 555s, and these four here form a delay line. So actually the last half of this one plus these give us 8 different bits. So they're all monostable. They go high for a given amount of time. And what we have, if we look closely, there's some capacitors in between each stage, and they form a high-pass filter. What happens is when the falling edge of the previous pulse happens, then that capacitor will cause a falling a low value to the trigger of the next stage, which will trigger its monostable timer function. Now you can't just hook them up directly, because as long as the trigger is low, it will keep that output high, and because the stable state of the monostable configuration is low, then it'll just keep everything kind of on and not in a good state. So essentially you're making it negative edge sensitive as opposed to just low value sensitive. Okay, so why do we actually have 556s down here? Well, we do have a trigger for the start bit over here, since in RS-232 frame actually starts with a start and a stop bit. So the stop bit's kind of implied. We assume the user's not going to press this the trigger button fast enough for the stop bit to not automatically happen. And there's a little inverter over there because the RS-232 signals are active low. This was supposed to be the receiver, and essentially we use the same delay line, and the delay line the on times of the delay line were intended to latch in the various values coming into the UART in port. Now, as you can see, there's been a lot of rework. I had some logic errors with the diode logic here. I was making it an OR instead of an AND, without realizing that, of course, the monostable configuration output is active high, not low. And with that came the fact that I had to switch all the trigger and threshold inputs on the latches here, because they were the wrong logic, and I had to make this button over here active low instead of active high. Now, the big problem which cripples this entire receiver chain is my start bit detector, which is here. As you can guys see, there are 3 capacitors here. That's because I wanted to move the I wanted to start this delay chain 1.5 bit cycles later, so I could sample in the middle of the bits as opposed to just the first edge of the bit. Now, the problem is here that it detects the start bit great, but if there are any other bits, now more specifically, if there are any more low transitions in the transmission, well, the start bit detector will trigger these guys off again, and well, that's just not good at all. So you'll get, what you're normally supposed to see is a wave of delays going down this chain here, and instead you'll get 2 waves, and your latches will just all be messed up. So another issue is that these will latch at a low level as opposed to sample, which you really want these to sample on active low, on a falling transition, as opposed to just taking whatever happens when its input is is actually in this case high because we switched the logic here. So in any case, if you have any misalignment, it's pretty much going to trigger these latches. And if you kind of think through this whole circuit, I'll post the schematic. You'll kind of see why there's a big problem with that. I do think it is possible still with 556s, but you'll actually have to set these up as either double D flip-flops, or you'll need some input edge detectors, and you'll also need to do something about this guy, which is gate him based on whether the delay chain is going. Now that requires a lot of extra signals moving around, and at some point you kind of have to deal with the impedance matching between everything, which I've kind of been playing fast and loose with here. So when I go to test this, essentially this board runs on 12 volts, and there's a connector here where the power comes in here, and here we have a oscilloscope probe just hooked up to the UART output. Now, because it's 12 volts and we want to talk to a 3.3 volt FTDI chip, we've got a level translator here. Transmitter side is easy. You can see those three 10K resistors. You just put, there's actually 4, so you want to quarter the voltage. 12 divided by 4 is 3, and so you put 3 on top, 1 on bottom. Nice voltage divider. The rest of this junk is, of course, the receiver voltage translator. So we've got a 12 volt power coming in, and 2 inverters essentially. This thing sucks a lot of power because you gotta get those. You got to get the input impedance low enough such that you can kind of overdrive all this resistor crud that's going on. So yeah, because the receiver doesn't work, we're not using these transistors. So we've got this output of the level translator comes over to this jumper wires over to this FTDI cable right here. Okay, and so the baud rate of this guy will change as it heats up. It seems to get higher as it heats up, which I don't quite understand, since resistors should get higher resistance when they heat up, but maybe the semiconductors are experiencing thermal runaway or something. A multitude of effects could cause that. So I'm going to go ahead and fire up the oscilloscope program, and we'll see what the output looks like. Alright, so now I have the oscilloscope hooked up, and right now it's transmitting all zeros, so all you can see right now is the start bit. I'm going to go ahead and turn on bit 7, which will be the last bit transmitted, and you can see how long the message is. So there you go, bit 7's on, stop bit comes right after, and I mean, we can play with any of these bits and turn them on and off. So this here is, I got it right, there we go. This is OXAA, so this is just a square wave. You can also do OX55, that's another favorite. And with both OXAA and OX55, essentially we tested every bit on and off. So that's OX55. So one interesting thing there is to see is if you want to see kind of when the delay lines happen, I can basically probing each output of the 556s in the delay line. So there we go, that's the start bit. That's bit 1, bit 2, bit 3. So as you can see that they just kind of go off in a chain and trigger each other, and that gets ANDed with the switch selections that the user selects, and the user just presses a button to trigger that first start bit to go. Okay, so now we want to actually hook it up to the computer, and for that we need the baud rate, because you could calculate the baud rate out, but we've got resistors and capacitors with things like 10% tolerances, so who knows what your actual baud rate is going to be. So of course you really couldn't build this without a some sort of oscilloscope, I think, unless you're really skilled at the debugging of kind of bitwise errors. So way down in this corner we can see baud rate is about 9,000 baud.